Okay, our last speaker in the afternoon session is Dr. Lisa Su. And Lisa was a former student of Dmitry, getting all 3 degrees from MIT. And she has since had a very distinguished leadership career at IBM and Freescale, and is now the president and CEO of AMD. So I think it's my honor to have Lisa give her talk on multi-chip technologies.
All right, good afternoon, everyone. It's really a pleasure and honor to be here. Thanks to Hank for inviting me. And then I think on behalf of all of Dmitry's students, I have to say thank you to Dmitry for everything that he's done for us and done for the industry. So I will say that my talk will be a little different than all that you've heard today, because one of the things that was quite unique about Dmitry's research groups is he would go from the, I would call it very advanced, maybe slightly esoteric, like Dirk mentioned some of the quantum stuff, to the perhaps a little bit practical, closer to industry, what's going to product over the next few years. And so I happen to always be on that side of it, but it's really a pleasure to be here to help celebrate Dmitry's retirement. So I'm going to talk a little bit about high-performance computing and what we're doing in terms of really extending high-performance computing over the next 5 to 10 years. And I would say that all of the stuff that we've heard about today is all additive. This is really how do we put things into products. So a little bit about just how exciting the industry is. I think Thomas said it. I mean, it's a really exciting time to be in the semiconductor industry from the standpoint of all of the applications that warrant more and more computing horsepower, whether you're talking about in the cloud or in automotive or in artificial intelligence or in edge applications. All of those things require high-performance computing and really pushing the envelope of where technology can go. And I remember when I was at MIT, it used to be, hey, can scaling get beyond 10th micron? Like 10th micron was like the big deal. And now we're talking about sub 5 nanometer as where we are. So why is it so exciting? And again, I think all of us know these things, but it's kind of staggering when you look at the numbers. You see incredible amount of data that's growing. So let's call it 50x more data over the next 5 to 7 years. And we're all generating this data, but we don't know what to do with all this data. So as Dario said, with all of the interests around machine learning, artificial intelligence, how can we more actively use the data that's coming to bear? Connectivity, intelligence at the edge, these are all some of the key trends that are giving us a lot of motivation to keep pushing the envelope in technology. From my standpoint, I happen to be focused on processors, and so I'll talk a little bit about processors and where processors are going. The key elements from the processing standpoint are in CPUs and GPUs, right? So CPUs are the general purpose processing unit. And whether you're talking about big data or high performance computing or machine learning, you need CPUs. But you also need GPUs as well as accelerators. And people used to say, what are you going to do with that extra bit of computing horsepower? And now nobody says that. Everyone's on, how can you give me more? And how can you give me more faster? And how can you give me more cheaper? So in that context, what we did was just take a look at what have the trends been in high-performance computing, over the last 10 years. And it's kind of interesting. You can plot almost all kinds of data, and you can draw some kind of line through them. And so, I'm just going to show you a little bit of data. And this is actually historical data over the last 10 years on, CPU and GPU trends. This is including certainly some AMD data, but also all of our competitive data from Intel, NVIDIA, and some of the other key players in the industry. And like I said, you can draw a straight line when you look at how much performance you get per a couple of years. And on the GPU side, we measure single precision floating point. On the CPU side, we measure throughput. But net, This is putting everything together, process technology, architecture, system technology. You can see that we've been doubling every 2.4 years. And that's taken a lot of hard work. Like it's really, I would say, all kinds of things coming together from that. If you try to break it out into system level performance, what you see on a system standpoint, you see kind of very similar trends. So similar trends in terms of we are able to increase performance every couple of years, but it takes a lot of work and a lot of tricks to do that. Now, from a technology standpoint, since many of us are device people or started as device people, it's gotten hard, right, to get the device performance. And so, device performance has given us a piece of the answer. And I would say that, today, it's pretty amazing what we've been able to do with FinFET technologies in the 16 and 14 nanometer generation as we move to 10 and 7. It is pretty, pretty amazing. But it has required just a tremendous amount of innovation on the device side to contribute to this performance improvement over time. And when you kind of add it up, we actually tried to quantify the various pieces of the performance enhancements that you've seen in high performance computing over the last 10 years. And I wouldn't say that this is 100% exact, but I think it gives you a pretty good feeling of the pieces of the puzzle to keep computing on its exponential curve, right? So, process technology gains about 40% of it, and that is including die shrinks, including transistor performance and density and all of that stuff. We've also, as an industry, innovated in many other areas. So, from a processor standpoint, a lot of innovation on the microarchitecture and on power management techniques and on compiler techniques to try to advance the overall performance capabilities. And then just pure brute force, just using more power, more power and just using more die size than you had in the past, have all contributed to kind of where we are today. And so this kind of gives you the idea of as we're looking at, what do we need to do for the next 10 years, there are a lot more, sort of pieces to the puzzle. So now when we look at some of the barriers to continued performance improvement, I think this gives us, some of the things that we have to work on. So, starting first with just, power and the power in these systems. I think somebody was asking how much power can you dissipate earlier. When you look at our high performance processors or GPUs today, I mean they're really dissipating up to 300 watts of power on a single die. So it's pretty hot, and we've increased that every couple of years, but you do reach some type of physical limits in terms of how you can cool silicon in that area. And what you notice is the makeup of the power is only about a third pure computation, right? There's a lot of the power that's going to the I/O. There's a lot of power that's going to the fabric. There's a lot of power that's going to the caches. And so you can see the efficiency of the power that you're using is less than you might expect. And then you also look at die size. We all like building very large chips. And so I think the idea of going from sort of proof of concepts to let's call it small chips. I call small chips like IoT type chips, and then really big chips like what go into sort of high performance processors. We now see the largest GPUs and CPUs up over 600 millimeters squared, and I guess really getting to the point that we're reaching the reticle limit of what you can print. And so again, we see these as some of the limitations of continuing to improve the performance. I think Moore's law continues to be something that everyone talks about. Is it slowing down? Yes, it's slowing down. Is it still important? Yes, it's still important. The question is, how do we get as much performance out of each node. We are getting density, but we're not getting as much performance in each node. So, from an economic standpoint as well, I think the other piece that's important is as we go to these smaller and smaller dimensions, there are actually fewer applications that can actually afford to use these leading edge technologies. So when you go from, let's call it, you've seen a steady increase in, this is a cost per millimeter. So if you think about, just die cost, it's not cost per transistor. So cost per transistor is continuing to get better, but cost per millimeter is, getting steadily worse. And you can even say that, in the 7 nanometer generation, because of all of the, quadruple patterning and, very, complex process techniques that are in place, that the physical, processing steps are such that the cost per millimeter is increasing. And so that also says where are you going to get your performance and how do you gather, sort of the performance in the most economical way. So take these as, some of the things that we think about, as we are thinking about, sort of what should the computing roadmap be over the next 5 years. And, we really come to, the point where, we do believe that new approaches are needed, and new approaches come in various different flavors. The one that I'm going to focus on is what we can do in terms of, really multi-chip technology, because we think that that's exceptionally both manufacturable as well as scalable in terms of computing. And so when you look at, some of the things that we can do, the question is, how do we take our current trajectory and overcome, some of these challenges that I mentioned in the area of power, die size, cost, and overall bandwidth. So, really when you look at multi-chip architectures, they've been around for a long time, actually. Lots of research have been done on them for many, many years. But they have, I think more recently become actually quite prevalent in not just simple applications, but I think much more complex applications as well. So just looking at the motivation for multi-chip architectures, when you look at high-performance server chips today, what you want is you want more and more computing power. And what that means is usually more cores, more cache, more area. And what we looked at when we looked at certainly where that should go, we actually said that, hey, the most reasonable way to do this is to break this up into multiple chips. And the key in doing that, frankly, is the fabric technology and making sure that the interconnection between the chips is high enough speed that it doesn't limit your computational capabilities. So an example that I can give you is when you look at today's server processor chips, we're running about 32 cores per, let's call it, system die. And if you did a 32-core die in 16 or 14 nanometer technology, with everything that you have to put on it, it's probably about 700 plus millimeters squared. That is not a very manufacturable chip. It's certainly high cost. And when you look at the alternative, which is to implement that in a 4-die multi-chip module, you actually do pay a little bit of overhead. So the overhead is probably about less than 10% or so. But you get incredible scalability, because now instead of building one chip at 700 plus millimeters squared, you get to build 4 at a much more reasonable die size. And in addition to that, you get to decide how much computing do you really need in your application. And so this is a real world view of the current state of the art for CPU technologies, and it provides quite a bit of flexibility going forward. So this was as of last year. Now moving forward, I would say there's a lot more that we need to do with multi-chip technologies, and now when we look at some of the memory integration problems, bringing memory as close as possible to the processor gives us a lot of performance enhancement. And I think 2.5D memory integration is one of those cases. So if you look at, sort of the technology, several years ago, you would have, a processing die, a graphics processor surrounded by lots and lots of memory, on board. And, frankly, you can look at the size of that board. It takes up a lot of board space and thus, reduces your performance capability. Whereas with high bandwidth memory and really, stacking the memory with an interposer, you can get, a much tighter, higher bandwidth, lower power, more integrated solution. And this actually has been in production for some time, but it's actually, again, it's at a point where technology has been demonstrated, but getting into the, multi-tens of millions of units of production is, it's still at a manufacturing cost point that is higher than perhaps you would need it to be. But this gives you one idea of the direction that multi-chip technologies can take. And I think the more interesting thing is, what can we do after this, and what can we do in 3D stacking? And I think there's a lot of excitement around this, especially if you're stacking, products with or chiplets with differing technologies. So, digital plus memory plus it could be some other, power management capabilities. And so, the idea with, 3D integration is how do we bring even more capability closer to the processor in a smaller footprint, at less power. And so if you think about, I talked about 2.5D integration being good for memory. Going to 3D integration, we can significantly increase the bandwidth of the solution, as well as reducing the switching power. Now, when you look at what you can do with this technology, and maybe this is some of what has been talked about earlier today, you can imagine now stacking CPU plus GPU, plus non-volatile memory plus DRAM in various configurations, and really building out the full system capability there. So, from the standpoint of where the technology is, I would say we're not quite there yet. I think we can get there over the next couple, whether it's 3 years or 5 years, depends on how quickly things go. But there are a lot of challenges just relative to how do you get again the interconnect between all of these various pieces to a point where you don't lose more than you gain in this process. But again, these are all elements that will help us in that increasing performance over the next 5 years. So, when you look at other things that are interesting, I think we're all interested in system-level architectures and how we can build better system-level architectures. And from that standpoint, just to give you an example, I believe that the future systems will have a combination of CPUs, GPUs, ASICs, FPGAs, accelerators. And whether you're doing a deep learning application, or you're doing an inference application, or you're doing just a traditional high-performance computing application, you will have different pieces of those different types of processing being integrated together. And so how we interconnect these in terms of making the interconnects as simple as possible actually leads to a lot of the performance enhancements. And if you look at traditional architectures, there are a lot of switches and things that you have to put into the system because that's the way things have been built. And what we're doing today is really building a lot of those interconnects right into the main processing die, such that it's much more efficient and you have a better ratio between computing and I/O and memory capability. And so my point with all of this is that, hey, you need to do it all. Right? We need to do every piece of this integration to keep the performance roadmap that we want. And that's where we go to the fundamental process technology and materials. Very, very important. I mean, I'm actually excited that there's so much excitement about some of the next generation technologies. But in addition to that, we have to do all of the other things that are maybe 5 to 10% elements, but really, really important. So, looking at power management, looking at the microarchitecture, the software, the memory integration, the stacking of components, all of these are critical, for us to stay on that computing curve of, doubling performance, every couple of years. I think what you'll see is with some of the acceleration technologies, you can even be ahead of that curve. And for specific applications, you can certainly be ahead of that curve. But for the general purpose computing, you need to be able to run a lot of code. And so there's quite a bit of I would call it overhead. And that's why we have to do each one of these pieces in terms of overall innovation. So, with that, I would like to, kind of just maybe conclude and say there are a lot of exciting things that we're working on in the industry today. From our standpoint, there's never been a higher demand for computing in the industry. And if you look at each of the pieces, I think multi-chip architectures can be a big piece of it. I think material and process enhancements can be a big piece of it. I think what we can do together in terms of the system architecture, are big pieces of it as well. And so, we'll continue to work on these areas as you guys continue to work on the research, to move things forward. So with that, I think, Mark, I'm within my time. Thank you.
So we do have time for questions, although we do have a panel session that'll start at 4. And frankly, I think it might be better just to leave the questions. Well, let's ask 1 or 2 questions now, and then we'll leave the rest for the panel. Go ahead.
With this enormous explosion in data, what about security?
Yes, great question, Hank. I would say security is front and center of everyone's mind. And I think it's become even more front and center. It used to be something that everybody in the industry thought about, but there was this little group of people sort of in a dark room that worked on security. And now I think, certainly for us, but I know for our colleagues at other companies, it's front and center. It's when you're designing a microprocessor, how do you make sure that the architecture is secure? How do you make sure when you're designing firmware that the architecture is secure? How do you make sure you have the right holes? And by the way, it's never going to be 100% secure. I think we've kind of come to that conclusion that it won't be 100%, but if we can make it 99.9999, that's a good thing. But no question, you're right. There's a tremendous amount of focus on security. Ted.
Just following up on that, do you see yourself dedicating any silicon area to the security, or do you see it happening at the silicon or other material, but at upper levels?
We will dedicate silicon area to security. I don't think it's a lot of silicon area, but it is, we will make silicon changes to make the architecture more secure. And then on the software side, because I think that's where it's even more interesting. I think that there'll be a lot more of that as well. Yeah.
Go ahead, Carl.
Yes.
So there's we heard earlier about the experience that some of us had, working with transistors and forming like a personal connection with an individual transistor, like getting mad at one transistor. So we've had that experience probably, a lot of us. And I worry sometimes that the generation that's coming up now is never going to experience that. And one of the things I worry about when I see what you're showing us here in this big block, the CPU and memory, is that you won't even be able to kind of put boards into a computer anymore. You just buy a box and you plug it in, and it'll. And so I'm wondering, what happens to electronics when you can't, you can't play with it at the discrete component level anymore. And is AMD? I know there's a Raspberry Pi and there's things like that happening. Is AMD worried about that at all? Or thinking about it?
Well, Carl, since you mentioned that, can I tell you my personal transistor story? Okay. Because I think it's an appropriate personal transistor story because, like many of you who were students here, I did my PhD research in Building 39, and, we had our lab. I think it was in the 2nd floor at that particular time. I don't know where it is now, Jesus. Is it still on the 2nd floor? Okay, that was 20 plus years ago, just so we know. And we were trying to make really small transistors, right? I mean, we're trying to do some kind of, one way or another, get a 10th micron transistor, which was difficult. And my personal transistor story is, when I got silicon, from the lab, Dimitri actually came into the lab with me, and we actually measured our transistor, okay? And I thought, oh my God, does Dimitri even know how to measure a transistor? I mean, it was like, we were sitting there with the 4145, and it was fun. So, so yes, I share your personal transistor story. That being the case, I don't worry about that block, because I think what we're looking at is, I mean, we have plenty of people, in our company thinking about personal, sort of that transistor element or that element. But I think the idea of getting people really excited about electronics, I think, is important. And so the fact that you can get, now, gigaflops or teraflops of performance, for very, very, sort of cheap prices allows you to do a lot more than we could do back then. So, I think there's still a lot of learning that can happen. We have a whole bunch of people send me notes all the time about how they're building their first PC and they're getting to do, sort of their first computing tasks. So.
I have one more question, and then we'll start.
Yes.
The eve that comes out of putting all these different chips together, who takes responsibility for these? Because these might be different sources that are giving you these chips, and each of them might be yielding chips, but once it's all put together, there's a chance that there will be
Yes.
yield loss. So who is going to be responsible?
Yeah, that's us. Yeah, that's. No, I think that's what some of the challenges are, which is the technology capability for doing this integration was probably there 10 years ago, but the manufacturing infrastructure at scale was not necessarily there. And so it's gotten a lot better. It's gotten a lot better, but I would say that large system companies now, instead of necessarily thinking about yield on a single die, will think about yield on their completed module and every step of the way. So.
All right, last one. Keep Lisa on the hot seat here.
Same point. You have all these different people providing these chiplets. So what if one of those contaminates or there is some sort of a hardware vulnerability in it, and who takes responsibility for it? Especially with these non-volatile memories, everyone talks about them. They have the data in them, so that even if it's powered off, someone can read it. Who takes responsibility for that? And how do you mitigate those issues? This is not about cybersecurity. This is more about someone stealing your hardware.
Yeah, you're talking about physical security?
Yeah.
Yeah, I think it's the same answer. I think it is the system provider's responsibility to make sure that all of these things work the way they're supposed to work. And so, back to the earlier question, I mean, we will put certain logic in place to try to ensure that the physical security of these chips are in place. But yeah, I think that's, again, that's some of the different levels of innovation that have to happen when you're actually thinking about putting these things together. So.
Okay, let's thank Lisa, and then first.